For our final video, we're going to be exploring the topic of organometallics, and this is where organic and inorganic chemistry meet. So we're going to be focusing on how we can build interesting organic compounds using transition metal catalysts. What I'm going to encourage you to do as we go through a few of these reactions later on in the talk is to think about how there's really not a good analog to doing this using traditional organic chemistry. I would say organometallic chemistry has really revolutionized organic synthesis over the past 20 or 30 years. You won't be able to find too many syntheses in the modern literature that do not use a transition metal catalyst. In order to understand the way that these processes work, we need to first understand the fundamental organometallic transformations. These are the kind of different steps that we have access to when we're thinking about how we can build and construct molecules. So we've broken these down into 5 different patterns, right? We can categorize these based on the changes in bonding and the changes that are occurring at our transition metal catalyst. The first of these steps or types of reactions is what we call an oxidative addition. This is formally where a metal inserts itself into a sigma bond of a compound. And ultimately, what ends up happening is the oxidation state of our transition metal increases by 2. Right? In the schematic that's drawn here, we go from a 0 oxidation state in our starting material to a +2 oxidation state in our product. And so oxidation again is the loss of electrons, meaning it's becoming more positive. So again, that's where that term oxidative addition comes from. The microscopic reverse of oxidative addition is a process called reductive elimination. And so this is the exact opposite of what we see in our oxidative addition, where we're going from a metal that has 2 different X-type ligands on it, and it removes itself from those X-type ligands, forming a sigma bond, in this case between atom X and atom Y. Again, this is just the opposite of what's occurring with oxidative addition. And we can see here that the oxidation state of our metal goes down by 2. Again, reduction is loss of electron or is gain of electrons, meaning it becomes more negative. So we can see here that that change in oxidation state reflects our metal becoming more negative. Our next fundamental reaction step is actually a combination. These are called insertion reactions. These reactions occur with no net change in oxidation state. Our metal initially has a single X-type ligand and an L-type ligand, traditionally either a carbonyl, like a carbon monoxide ligand, or an alkene, which is the pi complex. It undergoes this insertion pathway, the 1,1 insertion pathway or the 1,2 insertion pathway. 1,1 insertions happen on carbonyls, 1,2 insertion pathways happen on alkenes, traditionally. And so what happens is this X-type ligand that's initially attached to our metal moves over and forms a new bond to our carbon atom of the carbonyl. And then the carbonyl itself remains bound to our metal. We can see that when that X-type ligand transitions over to the carbon, our carbonyl now becomes an X-type ligand. So again, we don't have any formal change in our oxidation state for an insertion reaction. For a 1,2 insertion, this is where we again have our X-type ligand that forms a new bond to a carbon atom of an alkene, and you could think of this pi bond in the alkene as going back and forming a new bond to our metal. So again, our metal still only has a single X-type ligand in the course of this transformation. So there's no net change in our oxidation state. This is called a 1,2 insertion because we are creating bonds at both the 1 and 2 position of our alkene. A 1,1 insertion pathway is because we're changing bonds both at the 1 position. So our metal carbon bond and our carbon X bond are both occurring at the same atom. Our final 2 steps that we have to work with here are elimination and transmetallation. So the elimination process is really just the opposite of a 1,2 insertion mechanism. The most common case here is where X is actually a hydrogen, and this has a special name called a beta hydride elimination, because the hydrogen is located on the beta carbon away from our metal center. This elimination, again, has no formal change on our oxidation state, right? It's the same, it's the reverse direction of our insertion mechanism. And we end up reforming a pi bond right? And we have our metal that's bound to that X-type ligand. Our last step or type of reaction that we're going to look at for our organometallic section is what we're going to call a transmetallation. This is also called a sigma bond metathesis reaction if you are looking out there in the literature. And this is really just where two different metal centers can exchange their X-type ligands. And so we see here that metal 1 is initially bound to atom X, and after this process of transmetallation, right, the X and Y have now switched the metal that they are bound to. And so these are the 5 kind of fundamental reaction classes or steps that we're going to look at. And what I want you to be able to do is identify the patterns that we're seeing in these steps and name them. Right? If our oxidation state is going up by 2, more than likely it's an oxidative addition. If our oxidation state is going down by 2, it's probably a reductive elimination. If we see that we are doing those insertion pathways where we don't have a net change in our oxidation, right, it's either an insertion or elimination. Lastly, transmetallation is really just where we're swapping different X-type ligands between metal centers. So let's look at a few reactions and think about how these transformations can be strung together to create interesting organic molecules from relatively simple substrates. So the first reaction we're going to talk about is the palladium catalyzed cross-coupling reaction. This class of reactions has actually been hugely instrumental in organic synthesis, to the point where it is one of the reactions that received the Nobel Prize in 2010. This process, we're going to start at the top of our catalytic cycle, where we have a square planar palladium complex. This undergoes a transmetallation with some metal R2 ligand, right? So R2 just being another carbon atom. And what happens is we exchange R2 for whatever this X is, right? So we can see that our second metal here is just picking up that X ligand. That leaves our palladium with R1 and R2. After this step, we have again a square planar complex, and it can undergo a reductive elimination to give off R1 and R2 directly bound to each other, and we're left with our palladium with 2 different phosphine ligands. In the presence of R1 bound to a halogen or a different kind of compound, normally these are halogens, we can see a final oxidative addition to get us back to the starting point of our reaction. Now, if we're thinking about what we can do here, right, this is a way that we can directly couple R1 and R2. This is something that would be very challenging to do for most traditional organic reaction mechanisms. As we're talking through these, right, I have a little cheat sheet over here on the right of these different types of reactions as we're going through. So please pause the video as needed to review these reactions and see if you can see how our changes in our metal center are reflected in these kind of fundamental transformations. As I alluded to, this particular reaction was one of the key components in receiving the Nobel Prize back in 2010. There's a wide variety of this second metal that can be employed, and actually a number of named reactions have come out of this. So this is not a table that you have to memorize, but it's something that is kind of a nice reference if you're ever doing synthetic organic chemistry. So depending on the nature of that metal and the nature of R2, there's actually a wide range of these different named reactions. So if our metal is actually a boronic acid, this is what's called a Suzuki coupling. If it is a zinc compound, so it's another zinc metal complex bound to whatever our R unit is, this is called a Negishi coupling. A very interesting version of this is called the Sonogashira reaction, where we use a copper catalyst that actually is bound to an alkyne, so a C with a triple bond on it. I actually ran that reaction quite often all throughout grad school, so I'm well acquainted with Sonogashira reactions. If we use a Grignard reagent, so again a magnesium bromide or alkyl magnesium bromide, that's what's called a Kumada coupling. And finally, a Stille reaction involves the use of tin reagents. All of those are different variations of our metal bound to R2. The core part of this transition metal catalyzed reaction with the palladium doesn't change, right? It doesn't change regardless of which metal we use for our transmetallation step. So this is our palladium catalyzed cross coupling that we can break down into these 3 different steps. Let's look at something that has a couple more steps. And again, I want to re-emphasize how these reactions allow us to do things that we could not do using traditional organic chemistry. The second reaction we're going to talk about is the Shell-Hire olefination process. So this was actually developed by Shell, the oil corporation, and it is a commercial use for ethylene, right? So C2H4. This is a compound that's a gas, it's hard to store, and it's hard to transport. In fact, this small molecule used to just be burned off because that was far easier than actually using it for anything. So instead of burning off this molecule, Shell developed a process to convert this into longer chain alkanes that may be used for fuel or at least just for storage of ethylene. So we're going to start up here with our nickel hydride complex in the middle, right? This is the complex that we begin with in this reaction cycle. It has a bidentate ligand framework that's attached to it. Ethylene can undergo a ligand association. So this is kind of a boring step. This is something we've already seen, where essentially we're just saying a ligand gets close enough to form a bond to the metal center. Following this ligand association, right, there's a next step. And so what I want you to do is we have this entire process written out in front of us. We have our cheat sheet on the right-hand side here. I want you to just take a second and see if you can classify each of these reactions, right? We have ligand association, which is again just a ligand coming in and touching and associating to the metal center. We have oxidative addition, reductive elimination, our insertions, elimination, and transmetallation. So try to assign each one of these steps one of these labels. So go ahead and pause the video and just take a swing at it and see if you get it correct. Okay, so let's go through these one at a time and see how they work. So we are here at our nickel complex that has a pi system that's directly attached. If we see a pi system attached to our metal center, we can assume we're probably going to be doing some kind of a 1,2 addition. That's the only one of these reactions that starts with a metal bound to a pi system. And sure enough, we can see that that hydrogen, in fact, is inserted onto our C2H4, and we form a new bond between a carbon and our nickel center. Following this step, we can have an association of another alkene, right, another unit of our ethylene for our ligand association. Now again, if we have an X-type ligand on our nickel, and we now have a pi system bound to the nickel, this fits all the patterns for doing yet another 1,2 insertion reaction onto our alkenes. At this point, right, we could have further olefination if we had more ethylene that came in, but at this point, to represent what's going on here, we can actually have one final step. Now I can see here that I'm going from a nickel that is bound to a carbon atom to a nickel that is bound to a hydrogen. I have to regenerate my catalyst. And so what's going to happen here is I'm going from an alkane to an alkene. The only type of reaction that we have that can do this is actually our elimination method or elimination step. And so this should not say reductive elimination. This should say our beta hydride elimination. And so this beta hydride elimination step regenerates our active catalyst and leaves us with an alkene. So this is the Shell-Hire olefination process. So it's a nice, few steps here that we can explain using our traditional organometallic methods. And the interesting thing is it allows us to combine multiple units of a reagent that used to just be burned off and thrown away into something that is a value-added product. So we're going to look at one more of these in the video, and then we're going to have a lot more of these to practice on in class, or at least a few more, that we can try to identify these fundamental reaction steps. So the last reaction is the Heck reaction. This is another one of the palladium catalyzed cross-couplings that was a part of the Nobel Prize in 2010. So that was actually awarded to 3 individuals for their contributions to the field. Again, we start with a palladium catalyst that undergoes an oxidative addition to get to our palladium square planar palladium complex. So just like on the last slide, what I want you to do is try to take a second and analyze these steps to get all the way back around to our initial palladium intermediate using these labels of oxidative addition, reductive elimination, insertion, elimination, and transmetallation. So pause the video and take a swing. All right, so we're at our square planar palladium complex. So what is it that we're seeing occur as we go from this complex down to the one on the bottom right? Well, again, this is our simple ligand association. A ligand is coming in and is binding to our metal center. If we have an alkene that's bound to a metal and we have X-type ligands, we can bet that our next step will be a 1,2 insertion, right? And in fact, that is what we see here. Our palladium has formed a bond to this carbon, the alpha carbon of our carbonyl, and our R group has ended up on that beta carbon of our carbonyl. Now we have an opportunity, or now we are at this palladium carbon bond. And one thing that's important to note about palladium, palladium absolutely loves to do beta hydride eliminations. So our elimination step comes next, where we can regenerate an alkene that leaves our metal complex by pulling off one of the hydrogens at that beta position. Now we're left with a palladium that is bound to a hydrogen and actually an X group, not an R group. And so once we are here, we undergo one final reductive elimination step to kick off HX and regenerate our active palladium transition metal complex. And so this is the Heck reaction, and we can analyze these using these fundamental reaction types. So what we're going to do in class is look at a few more of these transformations, a few more of these catalytic cycles, and try to analyze step by step what is going on and how can we label these different steps in our transformations.